में नहीं है भाई। जब सर ने परमिशन दिया तब स्टार्ट किया। जब सर ने परमिशन दिया तब स्टार्ट किया। हाँ, दो ही लेक्चर हैं। नहीं, नहीं।
Okay, plenty of information. This is the summary of the last class. We started by saying that what is the single pulse. A single pulse you can think about collecting a charge, but the detectors are operated either in the current mode or in the pulse mode. There is the mean square voltage mode which we did not discuss. Now the current mode, as you remember, it is average over many pulses. The response time is much larger than the collection time. So I naught is what the average current which flows. I naught is not about a single pulse. I naught is averaged over many pulses, which means I naught does not retain any information about the individual pulse. Individual pulse means the information about the charge and hence the energy. Individual pulse means the time over which it is collected. Generally it is useful for highways where the pulses are overlapping, in which case we won't be able to distinguish pulses anyway. The pulse mode is the one in which we generally operate our detectors. It provides well-resolved distinct individual pulses as the output across the resistance. Remember the resistance which we made. It retains energy time information. Remember that RC time constant much greater than the collection time. The pulse amplitude, the max. There are two voltages which are there. High voltage which we are applying, a DC voltage. A pulse which is coming across the resistance, the output voltage. Generally this V is a function of time, which is the output one. The maximum value I am calling as the amplitude. That amplitude is when all the charge is collected. So pulse amplitude basically is nothing but the charge collected by our detector. Its rise time is completely detected by detector and its fall time is completely detected by the RC circuit. Larger the value of the R, correspondingly different is the decay constant. Now make sure that you do the same thing for tau less than Tc as well, which is given in the book. In case if you do not understand it, you are going to let me know. It is generally useful in the low rate environment because we are able to get well resolved pulses. So what's the job for today to begin with is just to plot this pulse amplitude as the function of voltage which we are applying. This HV is the applied voltage. Yeah. So this is the plot which we asked in our Viva. So I am just using this Vmax. Yeah. And then I am going to plot it. So let's just see how it goes. By this time you already know that this okay, so I am dividing the entire plot in regions. There exist 6 regions. And understanding the detector, gaseous detector, is about studying those 6 regions. Yeah. The regions which we generally do not use for detector operations are these two and this one. So I am going to name them, of course, soon. But make sure you understand that region 2, region 3 and region 5 of our operation is what we generally use for detector purposes. However, the entire gaseous detector's understanding is built upon understanding this plot. The plot is done for the pulse mode. I am just tracking the pulse amplitude. Remember what was the pulse amplitude?
B max by
This guy. I am just tracking this value. Which means every time you are increasing the voltage, your entire pulse might be changing, but whatever is the maximum value is what I am tracking. Yeah? So sometimes in the advanced lab, teachers ask more about how the pulses change. And then they ask you how about these individual pulse amplitude. Why pulse amplitude? Because the pulse amplitude V max retains the information of the charge, which means the charge collected is what we are plotting. Sometimes it is written as the pulse amplitude, other times it is written as the charge collected. It's not the plot of the counts. It's not. We have just collected charge. We have not given it to any external circuit for any further processing. It's the plot of charge collected of pulse amplitude. Remember, never is it relate count, not it is direct plot of the counts versus voltage. Now it is fine, right? So our job is to understand these 5 regions, and we will be concentrating more on 2, 3 and 5. So let's just start with region 1. What happens if we do not apply any voltage? What will happen? कुछ भी voltage apply नहीं किया है, particle pass हुआ. What kind of particle? What kind of particle passes through it?
radiator.
Gaseous detector. Principle is based on ionizing particle passes through it, which means it ionized electron ion pairs. But I did not apply voltage. What will happen?
Not collected. No pulse.
No pulse because so this is the region where recombination dominates, which means at 0 volt, when we are not even applying any voltage, there is not even a combination. It's basically the recombination. Recombination of electrons and ions which are separately generated. They ultimately have their diffusion, thermal motion, and after that they will recombine. Yeah? And the recombination means that no charge will be collected, and that is the starting point here. The region which is 1 is what we call as the recombination region. So we call it by this name. Because as soon as you start applying the voltage, there will be electric field developing across the detector. What will be the job of the electric field?
Collect the charges.
The job of the electric field is to ensure that the electron drifts towards the anode, right? And positive ion drifts towards the cathode. The word drift means that the electron will gain energy from the electric field, but then it encounters one neutral molecule or ion, and because of that there will be some scattering. Over the period of many such events where the electron is gaining kinetic energy and losing through these Coulombic processes, it results in acquiring some sort of a uniform speed which we call as the drift speed. Yeah? That drift speed happens under the portion of this electric field. The electric field is because of the voltage applied, which means there will be a combination, there will be a competition between the recombination and the drift. So now there exists the competition. Between recombination and drift. This is the region in which as you apply some voltage, some of the electrons are not recombined and then they reach the respective electrode. So electron reaches here, positive ion reaches there, and in that case a little pulse comes, a small pulse comes, and the charge collected is corresponding to that charge, which is few electron ion pairs collected. As we are increasing the voltage, what is happening? The electric field starts increasing and the competition starts favoring the drift, such that by the time I am entering into the second region, I will have all the electrons drifting across under the action of electric field and recombination is negligible. So the first region is the direct competition between recombination versus electric drift, and the drift of the electron and ions is because of the voltage applied. So this region, as you can see, even though when I draw it, it looks like a linear one, but you never know how much there is a difficulty in figuring out how much charge you will be collecting at any particular voltage, because recombination process is a tedious process, a complex process. So the region is actually quite non-linear, and the non-linear regions we do not use for any purposes. And anyway, the charge collected is so small that I cannot do much, because I'll have to amplify a lot. So this region is not used. The region, it shows the competition between the recombination versus electric drift, and the region basically merges with the second region at the point where all the electron ion pairs which are generated are collected. Which means now as soon as I start entering into my region 2, since all the charge generated is collected, I will start getting information about all the charge which is generated is collected. So charge generated, the entire charge collected or generated is because of what? It is because of the charge generated is because of the energy loss.
Yes, sir.
Which means that in this region, the second region which we call as the saturation region, this is called the recombination region. Chamber is the word which is given, so is it? This is the region in which almost all generated charge is collected. Earlier charges were generated fully, but they were not getting collected. So that means you will start thinking about two things: charge which is generated, charge which is collected. In this region, charge generated is greater than charge collected, right? And it is the charge generated which is due to what?
Losing
That energy loss. So which means this gave you something like N naught E. But since I did not collect the entire charge, I will not be able to understand what was the energy loss exactly. Yeah? As soon as I enter here, Q generated becomes equal to collected.
Yes, sir.
Now at this region, I start getting information about this primary ionization and not Q. So the entire primary ionization is collected. So this is a very good region for doing the energy measurement, because N naught is the first thing which happens entirely because of the energy loss, and that's the charge which we are going to collect. So the second region, which is the saturation region, it corresponds to the region where the drift due to electric field wins the competition handsomely. Recombination becomes almost negligible, and the region is very useful for energy measurement, energy measurement is what we call as the spectroscope. So, region 2, which is the ionization chamber region, is what we use for our spectroscopic purposes. Now, if this region becomes useful, then why do we go further? The only flip side of this region is that even though I am collecting entire generated charge, but as we will do it in our tutorials, the actual peak, which is the pulse amplitude, is quite small in microvolts. That means I will have to amplify this microvolt voltage in order to actually see something happening. So I do need immediately after this ionization and collection some sort of amplifiers, because without amplifiers the voltage is so small that we wouldn't be able to even detect properly. So the only flip side is this amplification. Yeah. Everything else which we did the discussion on, what will be the total voltage seen? Total voltage seen is, sir, Q by C. Q is what? N naught E by C. N naught is what? Delta E by W times divided by C. So make sure that whatever discussion we were doing is actually valid for our saturation region or the ionization chamber. Ionization chamber is still seldom used for our energy purposes, measuring purposes. We do not use it. We use the next region for some obvious reasons, but the downside, which is the amplifiers. Every time an amplifier will come, I have to worry about the linearity of the amplifier, whether amplifier is amplifying faithfully or not. Yeah, but it is still a very good region where N naught exactly corresponds to the charge generated. So people are using it. In some applications, people are using it. For example, if I give you a source and I ask you to calibrate, what is the meaning of the word calibration? Calibrate. So remember, we get energy only for distinct particles. We get alpha particle energies of 2 MeV, 3 MeV, 5 MeV, but we do not get continuous energy 2, 2.01, 2.02, 2.03. We do not get those kind of energies. How to figure out what will happen at 2.05 MeV if I have information about 2 MeV and 2.5 MeV? So I'll have to draw some curve interpolation. But for drawing that interpolation, I should be knowing my values of the energy pretty confidently or precisely at the 2 points, 2 MeV and 2.5 MeV. Any changes there, our interpolation will start giving wrong results. So whenever we want to calibrate our detector, which means what is the correct value of the output pulse for the given energy, this region becomes very useful. The region also starts becoming useful in our current mode. I mean, I wouldn't go into those details because the next region is what we use for the spectroscopic purposes, mainly in almost all the nuclear physics experiments. In almost all, except for few radiation dosimetry applications, everywhere we use the third one. Questions related to the first and the second. Questions related to the first and the second. Okay, tell me in that case if you do not have anything. So let me think about the pulse amplitude. And I blow up this much region. I know that at some rate my ionization chamber is getting big, which means it's getting plenty of radiation. And that rate is R1. What does that mean? What does that rate mean? What is the unit of rate?
Per second.
Per second. So number of incident radiation per second. Now think about what will happen if R2 is greater than R1. So the same detector is exposed to higher rate. Do you think the same plot will be implemented implemented, exactly the same thing will come. Or what will happen? I have changed just the rate. I have not changed the energy. So activity of the source is increased, but the source remains same. So if cesium emits 662 keV gamma, it is still emitting 662 keV gamma, but now the activity has increased, so there will be lot of 662 keV gammas hitting the detector. How will the plot look like for the second rate?
Depending.
So graph will shift towards the upper side, that's true. Because Q collected is equal to Q generated at the saturation value. That is related with N naught. What is N naught? Delta E divided by W. Now that I have given you higher activity source, this number is going to increase, of course. But the interesting twist is not this. Interesting twist is that the saturation for this guy may not take place here. This will take place at a little higher voltage. What does that mean? For the higher rate, electric field wins over the recombination, but at a slightly higher voltage. At the same voltage, since large number of electron and ion pairs are produced, some of the electrons are still getting recombined. So the winning over recombination takes more voltage or more electric field. That's the only thing which I wanted to tell you, other than the point that it is a saturation, it is mostly saturated. It's just that if the rate increases, there is a slight shift in the place where it gets saturated. You may not see it in the plot which is given in the book, because in the book the plot does not show two different rates. The plot shows two different energies. Yeah. So that's the only additional detail which I wanted to give you before proceeding to proportional region. So questions on the ionization chamber or recombination?
Sir,
Yes.
In this that R2 is greater than R1, like R2 the rate is greater than R1. सर अगर यही चीज़ अगर जो हमने पहले किया था करंट मोड में, तो वहाँ पे जो हम देख रहे थे तो
जो आपका नंबर है,
हमने बोला था कि एवरेज इफेक्ट नहीं हो रहा था,
एवरेज करंट, लेकिन उस स्टेज में डबल हो जाएगा, रेट पे डिपेंडेंट था, R टाइम्स Q था।
हाँ, R टाइम्स Q था।
So अगर R टाइम्स Q है I naught, so if R increases it will increase. Current, average current did not depend on the response time of the emitter. कैपिटल D पे डिपेंडेंट नहीं था। But if the rate changes or the charge changes, तब तो चेंज हो गई।
सर एक बार एक्सप्लेन कर दीजिएगा वो कर्व ऊपर क्यों है?
वो कर्व इधर इसलिए आया क्योंकि recombination. So the only thing is recombination is not a simple process. I mean, just like I said, some of the electrons start getting recombined. Now, if the electron and ions are more, then that means that several, I mean, few of those electrons can still recombine. If it is less, then they are very sparsely limited, then they are basically getting collected everywhere. If they start becoming closer, that means lot of electrons are there, lot of positive neutral, lot of neutral molecules are there. Electrons will start also encountering positive ions. Positive ions drift slowly. Electrons drift fast, but the electrons which are let's say made towards the cathode, etc., they will encounter some of the positive ions. So they will encounter positive ions more in the case when the rate is high as compared to the case when the rate is low, because less positive ions are created and hence it may not take that much of the voltage. This voltage shift, I wouldn't say that it cannot be measured, but it is still small. However, that shift is there. So it just means that the recombination still continues for higher voltages. I need higher voltage to dominate over recombination. Anything else? Yes. is the following. It is ultimately devilizing the details. Their non-book completely, gives one complete chapter for ionization chamber. It keeps on writing about what are the further details, for example, how the detector's geometry starts affecting the saturation, etc. So I am not going there. I am just going only at the top point that how will this current change if the energy changes? How will this current change if the rate changes? So I am not going into the detailed geometrical portion, but I still want to tell you that it will be the function of incident rate. Yeah, I will be drawing another energy particle soon on the top of this. Rate is something which I still want to do. Yeah, so there are minor effects. For example, you will think about whenever I am making some electrodes, the electric field at the edges, it cannot be uniform. Howsoever uniform you will try to make, the electric field at the edges will not be uniform. Which means that the electric field which I am considering uniform in a parallel plate device, even that is not uniform at the edge. And hence it will result in some distortion. So lot of time just goes into figuring out how to actually ensure that the uniform electric field is. So those are the kind of details which I am actually keeping you out from. So you will read only the relevant portion, not go beyond. We are into chapter 5 of the Knowles book, but from that chapter, we have already covered most of it, which is there in the first 4 or 5 pages. And after that, we are not even discussing.
Sir,
Yes.
Sir, in that curve, I am agree that कि कुछ हमको एक्स्ट्रा पोटेंशियल देना पड़ेगा उस रिकॉम्बिनेशन को और ज़्यादा डोमिनेट करने के लिए. तो सर वो तो जो हमारा कर्व R2 का ऊपर आ रहा है वो चीज़ नीचे R1 पे क्यों नहीं आ रही? मतलब वो तो ठीक है शिफ्ट
वोल्टेज में. ये रहा और कम होगा रे तो वो ऐसे हो जाएगा और बीच में होगा रे तो वो ऐसे हो जाएगा. इट जस्ट मींस दैट दिस गाय कीप्स ऑन शिफ्टिंग. It just means that nothing more. Remember, one of the things I do not even okay, it's very difficult for you guys to do that. Beta gamma is equal to 3. Was what? Minimum ionizing particle. Beta gamma is equal to 3. I asked you to do that in your tutorial. Now that number roughly equals 3. It's not exactly 3. It depends on the average ionization energy. So, if you have, for example, the same particle passing through different hydrogen, helium, lithium, so on and so forth, up to the lead, you will find out that beta gamma minimum ionizing particle goes towards slightly smaller. Now, this is something which you should be knowing at the MSc level. How exactly that is changing, we did not discuss, but we did discuss that it goes slightly less because the average ionization energy is different for different media. Yeah. So this effect is something similar. It's more of the qualitative nature. Given a question in which the rate 2 is higher than rate 1, which one will saturate faster? It's a question like this, a concept question like this. Because the recombination takes more time to be over. Now comes the most important region for energy spectroscopy. This is called the proportional region. And in this region, let's just devote some time figuring out what it is. As you can see, we have collected all the charges which are produced. If all the charges are produced, then how can my pulse amplitude increase? That's the first question which comes to the mind. And by this time, almost all of you know why it does that. What's the reason? Okay, so by this time the saturation region or the ionization chamber, we have collected all the electrons which were generated. Now the question comes, why the pulse amplitude increases? Remember, the pulse amplitude is proportional to the charge collected. So you can see that we are entering into the region in which the generated charge is less than the collected charge. The generated charge, remember, was N0 times E. So somehow the collected charge, since you have collected everything, should have N0 E, but with a factor M, which we call as the multiplication factor. And this factor starts between more than 1. And this factor remains in the region 10 raised to power 2 to 10 raised to power 4. That means of the order of 100 to 10,000. And when this happens, this is what we call as the proportional region. Now why that is happening is the question. The point is simple. We are going to get more charge, collected charge, than what was generated. Yeah? So, this factor comes. What's the reason? अरे अब तो आप कर चुके हैं भाई, काफी लोग तो
secondary ionization.
Say okay. So energetic electron.
Will collide and it produce secondary ionization.
Okay, so more or less I guess you already understand it, but let's just draw it just to make sure that we all understand the same point in the same way. So if I think about positive and negative terminal, and I think about a charged particle passes through it such that electron drift towards the positive electrode and positive ion drift towards cathode. Now, what happens is that when electron starts drifting, two things happen. One is it is drifting and then it's having Coulombic interaction with the ions which are there. Some of them also recombine, but we have already passed that region where the recombination was major effect. So now we do not need to worry about the recombination. Electron drifts under the action of electric field, having two words. One is it is gaining kinetic energy. Why it is gaining kinetic energy?
Due to the external potential.
Because of the electric field. So what kind of kinetic energy we are talking about? So if I call TE, kinetic energy of the electron, what will be that?
E times of E.
So it should be F times dx. Big deal. Yeah. What is F? Electric field is applied. EE. Since it's in one dimension, so I do not need to even write down the vectorial sign here. So kinetic energy is EE. What is this dx? Now you have ions everywhere, which is the gas ions. So how do we account for this dx? We say that there exists something called lambda, which is nothing but
Mean free path.
mean free path. So for the mean free path, the electron is gaining this kinetic energy. After reaching the mean free path, it gives part of its kinetic energy. Yeah. Now what is happening that the electric field is increasing because I am applying voltage, high voltage more and more. So once the electric field is sufficient, this electric field, this TE, which is equal to W. What is W? Average energy to create electron-ion pair. Once this electron's kinetic energy is sufficient, then this electron can do what? The primary electron which has come here now can release one more electron from here. Because it has gained sufficient kinetic energy from the field that it can exceed the average energy to create electron-ion pair. So from this point onwards, there exist two electrons. One, the original one which was moving, another which it has taken out from the gaseous atom. Now, as we keep on increasing or moving towards the anode, those electrons can also gain sufficient kinetic energy. The process starts becoming a cascade. So I am blowing it up in the region, but it is actually pretty narrow here. The whole idea depends upon what we call as the Townsend avalanche, that we have cascade of secondary electrons. What are we calling secondary electron? Each of the electron which is coming out, other than the original primary electron, I am calling out to be secondary electron. I am putting it in a word called cascade of electrons. They all start drifting towards the anode, and these electrons will now be collected, resulting in this multiplication factor m, which is greater than 1 in the region of proportional form. Now, another electron which was released will also do the same thing. Cascade another electron, that will also start doing the same thing. So you have plenty of avalanches going on. All the primary electrons which were produced, each of the primary electron will start creating its own avalanche, right? And what will we see, that the positive terminal, the anode, sees the multiplication factor m because of these many electrons getting collected. Each one giving a factor m. How many n naught is given? N naught times m. Yeah. So